Hello students, welcome back. We just completed section 1. Now let's go to section 2. Section 2 is a continuation of section 1. We are still in homomorphisms. This time, however, we are going to focus upon 3 important topics: image, preimage, and kernel. All 3 are important and difficult and time-consuming, of course. So I separated those 3 into a separate new section here, and let's begin that separate new section. Let's begin with a review. Let G and G prime be groups, and let phi a map from G to G prime. We say the map phi is a homomorphism if it preserves the group operation. As you can see from here, it's sending from G to G prime, and then the group operation A times B in G is preserved under this application of phi as phi of A times phi of B, which is in G prime. So that's a group operation in G prime. So blue versus red. Blue operation, red operation. Can you see that? And that has to work for any pair of elements A and B. Here's another way to write the same thing. A prime is a member of G prime, and that came from A. And B prime is a member of G prime, and that came from B, where A and B came from G. And consequently, A times B is a group operation in G. And phi is taking that group operation in G into the group operation in G prime, A prime times B prime. So phi preserves the group operation. And by the way, here we have universal operator. This is true for all A and B. Here we don't have the universal quantifier, but that's not necessary because we already have the double arrow. That means this conditional statement is a tautology. It's always true. So the double arrow includes this universal quantifier, and then actually vice versa. So you can rewrite the universal quantifier statement into double arrow tautology statement, and vice versa. This kind of statements can be rewritten with universal quantifier. You can always do that. I'm mentioning it here right now because I recently got a question about this from a student. Okay, where was I? Yes. Homomorphism preserves the group operation, and also remember this, homomorphism preserves the identity and inverse as well. And this is something we can actually prove, and we actually did it in section 1, so we're not going to redo it. Okay, there's a sketch. Please remember the results. Next, a bijective homomorphism is called an isomorphism. It's a bijection, so we have to consider the inverse map as well. You see, it's 1 to 1 around 2, so inverse is well defined from G prime to G. Interestingly, the inverse map is also homomorphism. The first half here means phi is a homomorphism, and that's part of the definition. The second half here is something we actually have to prove, and as a matter of fact, we did it. We proved it in section 1 already, so I'm not going to redo it. I'll just show you the sketch. In any case, remember the result. Okay, that was a quick review. Not that quick, but it's okay. I think it's time well spent, especially considering that I got a question from a student about those equivalent statements. Okay, let's go to 2.2, and this too is actually a review and preparation for what's to come. So for the time being, let's forget about algebra and algebraic structure, and let's go back to sets and maps. Let capital X and capital Y be non-empty sets, and let capital I and capital B be non-empty subsets of those X and Y, respectively. Okay, so all those are sets, non-empty sets. And then let's consider a map from capital X to capital Y. So not necessarily homomorphism or any kind of algebraic structure, just a map from one non-empty set to another non-empty set. And then let's consider two non-empty subsets, capital A and capital Y. Now, the image f of capital A and the preimage, this F inverse notation of capital B, are defined like this. The image is relatively easy to understand. It's a set of all function values f of a's where a belongs to capital A. Remember, this map f is sending elements of capital X to elements of capital Y, so the function value f of a belongs to capital Y. So this one is actually subset of capital Y. Okay? Now let's go to preimage. The preimage is defined as the set of all elements x from capital X so that the function value f of x belongs to capital B. Let's see. F is a map from capital X to target capital Y, so the function value f of x always belongs to capital Y. The question is whether that belongs to capital B or not. B is a subset, you see. So it's in Y, yes, but is it in B or not? And then the elements are actually coming from X, from capital X. So this is actually a subset of capital X. Now, one thing that you have to be extra careful is this notation. I use F inverse notation, and then frequently people read it as F inverse of B. And sometimes people even call it an inverse image. However, the preimage concept, or I don't like this term, inverse image concept, does not require the inverse map. If you go back to this definition here, the inverse map does not appear inside this set notation. It is just well defined with just F. So even though some people write as inverse image, I'll try not to use this term in order to avoid confusion, and I'll call it preimage all the time. So I'll try to read it as preimage of capital B rather than F inverse of B, but sometimes I may end up reading F inverse of B, but please understand that this is not necessarily the image of the inverse map. If the inverse map exists, yes, then they're the same. But the inverse map does not always exist, and even if the inverse map is not there, the preimage is still valid. Here is a visualization. The visualization of the image first. So this set capital A is mapped onto F of capital A, where this map is from R2 to R, and then it's a projection map, F of x comma y to y. So a bunch of dots here, x comma y, that share the same y coordinate value, will go to the same point here. So this is not a one-to-one map. The inverse is not well defined. In any case, we can consider the image like this. And you can consider 3D examples as well. Consider a 3D object and then put it under sunlight, and then you're going to get a shadow. And shadow is the image. If you do that under a flashlight, then these arrows will not be parallel anymore, because from the sunlight, yeah, you can consider those as parallel, but from flashlight, they're going to disperse away. And then if the screen is kind of curved, and then the image will be distorted even further. But in any case, that's where all those concepts and the term image and mapping, all those kind of terms were inspired. Another thing that you should observe here is you lost the dimension And in 3D example, again, 3D to 2D, you lost a dimension, and that can happen. And if you just have a curve here, then at least you do not lose the dimension, so dimension may decrease. And also, you may lose the cardinalities. If you have a bunch of dots here, and then several dots will go to a single point that share the same y-coordinate value. In general, we have something like this. If you take the image, as you move forward, the cardinality will decrease in general. They may stay the same, but sometimes they decrease. They will never increase. The proof is not too difficult, but this is algebra, so I'm not going to bother. Here's a visualization of the preimage. I set this example, f of x is x cubed minus x, and then my set capital B is this interval, highlighted in green. 0.2 to 0.5 right here, and then find a strip highlighted in green like this, and then find a portion of the graph that goes into the strip, here blue, and then here red, and then project those down to find intervals, blue interval and red interval. X coordinates are A1, A2, A3, and A4, and then you can find those by setting this f of x equal to 0.2 and solve that equation. You're going to get A1, A2, and A3, three solutions. And then set it equal to 0.5, you're going to get only one solution, one real solution. And that's going to be A4, and you're going to end up with this. So that's going to be A1, A2, and A3, A4, like this. And second interval is red in this picture, and the first interval is blue. And then also, in this particular case, we did not gain the cardinality, but if you consider a single point here, down here, and then it'll have three preimages, here, another here, and then over there. If you have a point up here, then it'll have only one preimage, nothing here, only one there. Again, we're going to end up with this. Moving forward, cardinality decrease. So if you move backward, then cardinality may increase, or they may stay the same. Again, the same comment. Proof is not too difficult, but this is algebra, so I'm not going to bother. And if you're interested, you can go back and restudy and review that Introduction to Proofs Plus or Analysis, or maybe you can request a new course in set theory. Okay, so much for easier part. And then here's a big deal. The preimage preserves all set operations: union, intersection, and inclusion. They're all true. They're all equal. The image, on the other hand, close but no cigar. Union, yes. Inclusion, yes. Intersection, not necessarily. So, preimage, all yes. For image, careful about the intersection. The proofs are not too difficult, but they do not fit the scope of this course. I mean, they must have been some challenging problems in the Introduction to Proofs course, or even in an analysis. Here, this is algebra, so let's not worry too much about that, but please be prepared to use these. Okay, so much for the preparation. In next video, we're going to talk about images and preimages in a special case when the map is not just map, but a homomorphism from one group to another group. In that case, things are a little bit different, and we're going to study those.